Now before we go on to the behavior of power series, there is something else I wanted to mention, and that is to ask what is the derivative of an analytic function. That is one more way of looking at the Cauchy-Riemann conditions, what these conditions are telling you. Okay. The derivative of a function f of z at some point z in the complex plane. So here is z and here is dz, z plus dz. So a normal way to define this would be to say that df over dz equal to the limit as dz as delta z goes to 0 of f of z plus delta z minus f of z over delta z. This is the normal way in which you would write down derivative. Okay. Now if this function, if you are looking at functions of a real variable, there is no problem because you start with some x, you go to x plus delta x and you divide by this delta x, take this difference and then you have a derivative. If you did it on the left, it would be the left derivative. If you did it on the right, it would be the right derivative. If these two limits are equal, then you call it the derivative from both sides. Now here, however, you have a little bit of an ambiguity. In what direction should I take this delta z? Should I take the difference between these 2 points, or could it be anywhere on the circle and I take these two or these two? What should I do? Okay. So let us take a very general case. Let us say that this delta z equal to epsilon e to the power I alpha, say. So the magnitude is epsilon and the direction with respect to a fixed reference direction is alpha. Okay. Then I plug that in here and I end up with, I work this out, I write z delta z as this and I am going to write this z as x plus iy, ditto here, and then work this out, write out the derivatives etc., and then it turns out that this becomes equal to I, it becomes equal to e to the power I alpha and then delta u over delta x cos alpha plus I e to the minus I alpha, because delta z is in the denominator. So this guy is going to come minus up there, plus I delta v over delta y sin alpha minus I times delta u over delta y cos alpha minus I delta v over delta x. Or something like that. Not sure about this sign here. Okay. So this is what this thing is, and now we got to go to the limit of asking, now we got to ask in what direction should alpha be. Okay. So one way to say I define the derivative of a function of a complex variable f of z is by saying that this thing here, this derivative should be the same regardless of which direction delta z goes to 0. So no matter how I approach 0 from any direction, I want to have the same answer. Okay. That is a reasonable thing to postulate, otherwise you do not have any uniqueness in the derivative at all, okay, because you have an infinite number of directions in the plane and you want to say it does not matter, can I ever have it independent of this alpha? So the next question is, when does this fellow become independent of alpha? And it is easy to check. The only time, the if and only if condition, it is necessary and sufficient that this whole thing be independent of alpha is if the Cauchy-Riemann conditions are satisfied. If this is equal to that, you take it out of the bracket, you get an e to the I alpha which cancels this, and ditto here. Okay. So this thing is independent of alpha if and only if CR conditions are satisfied. So that is another way to understand what is meant by analyticity of a function, to say that it has got a derivative and this derivative does not depend on the direction in which you take this limit, epsilon goes to 0. Okay. there is a bonus to this whole business, and the bonus is you have an infinite number of pieces of information here, unlike in stark contrast to what happens in the case of real variables. You can have, in the case of real variables, you know that you could have a function which is differentiable at some point, has a first derivative but does not have a second derivative, or has a second derivative, first two derivatives, does not have a third derivative, and so on. For instance, if you look at this function, if you look at f of x equal to mod x, this function does not have a derivative at the origin. It is a V-shaped curve, right. No derivative at the origin, no unique derivative at the origin, looks like this. How about this x mod x? How about that function? What would that do? Does it have a derivative at the origin, first derivative? Yes. Does it have a second derivative? No, it does not have a unique second derivative at the origin, because this thing here is equal to x squared if x greater than 0 minus x squared if x less than 0. So at the origin the slope is 0 from both sides, no problem, but this immediately tells you that what you really done is to take a parabola here and you joined it with a parabola here in this direction. So the derivative is fine, the function is 0 at the origin, its first derivative is also 0 from both sides. But the moment you go to the second derivative, you have a problem, because the curvature is different on both sides here. So that is an example of a function which is once differentiable but not twice differentiable. Now you can construct more and more such functions, you can add more powers and then multiply by mod x, and you will get functions which are 3 times differentiable but not 4 times, and so on and so forth. In the case of complex variables, that complication does not appear at all. The moment you say a function is analytic at a certain point, it means it has got a derivative. This derivative is itself an analytic function. Therefore it has a derivative which is an analytic function, and so on. So it means that every analytic function is infinitely differentiable at every point where it is analytic. All derivatives exist. That is a great simplification, enormous simplification. If f of z is analytic, implies that all its derivatives are also analytic in that region, this region. So you do not have the complications that you have in the case of real variables, functions of a real variable. This is an extremely useful property. Okay. Now what it means, what it implies immediately, is that you have a very useful representation for analytic functions in some region where it is analytic. You can always, if a function is analytic in some region like this, let us say it is R, this region here, then in general at some arbitrary point in this R, let me call it Z0, in general you can represent f of z by a power series about the point Z0, in general an infinite series. So you can represent it in the form n equal to 0 to infinity a sub n z minus Z0 to the power n, some constants times that. Okay. So every analytic function in general at any point of analyticity, except perhaps near boundary points or something, has a neighborhood in which you can represent this function by a power series in powers of z minus Z0. Okay. The question arises as to the convergence of this series, where it converges and so on, but before that we need to write down what this an is. Okay. What do you call such a series, by the way? It is a Taylor series. This is a Taylor series, right? So and what is the inverse formula for this Taylor series? What is an in terms of, if you invert this, how do you write an in terms of f? in any Taylor series, what is the nth coefficient? Yeah, it is 1 over n factorial dn over dz to the n f of z at the point z equal to z naught. It is the nth derivative at that point. Okay. Now, where would this series typically be finite? Where would it converge? Well, now I have to define what kind of convergence I mean. There could be convergence in the mean, there could be convergence, absolute convergence, there could be uniform convergence and so on and so forth, conditional convergence, etc. But let us talk about absolute convergence. In other words, if I take this power series and take the modulus of each term and add them all up, I want that to be finite. That is obviously the worst case scenario, because if you take the modulus of each term, there are no negative terms, everything is getting added up. If that converges, then of course if there are oscillations, it will be even better, it will definitely converge. So such a series, typically whenever you have such a power series, has a region of absolute convergence called its circle of convergence. So there is typically some circle. So for every power series, you give me a power series about a point z naught, a series of this kind, and there is some circle of convergence about this point z naught with a radius r, inside which, inside this region, summation n equal to 0 to infinity mod a n z minus z naught to the power n is less than infinity, converges absolutely inside. This is called the circle of convergence. This r is called the radius of convergence. Okay. Can we find r? How do we find r? Well, clearly it depends on how this series, how the nth term goes to 0. You need this thing to get smaller and smaller, otherwise it is not going to converge, right. So a necessary condition is that this thing must get smaller and smaller in absolute magnitude as n becomes larger and larger, so that the whole answer has a chance of being finite when you sum it, right. Now what is the formula for a n, for this radius r? Well, the simple ratio test for absolute convergence would suggest that this is limit n tends to infinity modulus a n over a n plus 1. Okay. And this r is called the radius of convergence. So all that we have used is a ratio test, which you know from elementary algebra. You know that if these things, if the ratio here is a n plus 1 over a n, if that is less than 1, then you have convergence, otherwise you do not have convergence, etc. You got to test further and so on. Okay. Now there is no guarantee that in all cases that this limit may exist, may not exist, this thing here. So we need a better definition, and a better one is r equal to limit superior mod a n to the power 1 over n. That is the least upper bound. So whether it has a maximum or not, limit or not, we do not care. This is the least upper bound of this mod a n to the power 1 over n. That always exists. It may be infinite, but if it is finite, you have a power series which is absolutely convergent inside here. What happens if this r is infinite? At some finite point z naught, here is a function for which I find a Taylor series, and the radius of convergence of this is infinite. What sort of function is it then? It is an entire function. The immediate conclusion is that it is an entire function, because everywhere there is a representation, a power series representation, which is absolutely convergent, so I can differentiate it term by term, integrate term by term, you can do whatever you like, you can rearrange terms and so on. Okay. So if r is infinite, you have an entire function. If r is not infinite, you have function with singularities, various kinds. What about this case, the exponential? So you have z to the power n over n factorial summation n equal to 0 to infinity, that was e to the z. All you have to do is to do the ratio test in this case. So an plus 1 over an is z to the n plus 1 over n plus 1 factorial n factorial over z to the power n. You take the modulus of this n plus 1 term divided by the n term modulus. If that is less than 1 in the limit as n tends to infinity, then I would say it is absolutely convergent. Now this z to the n cancels against this and gives you z, and there is a 1 over n plus 1. Now for all finite values of z, as n tends to infinity, this tends to 0, which is certainly less than 1, because there is a 1 over n in the denominator. So the conclusion is that the exponential series is an entire function, represents an entire function. E to the z is an entire function. The same thing is true for sine, cosine, etc., just by a trivial test of this kind. What about this series? F of z equal to 1 plus z squared summation n equal to 0 to infinity z to the power n. What about this series? Is this an entire function? It is not a polynomial, by the way, it is an infinite series. Is this represent an entire function? Where does this series converge? Mod z less than 1. Definitely it converges only for mod z less than 1. So it is clear that for mod z less than 1, so radius of convergence r equal to 1 in this case. Mod z must be less than 1. If it is greater than 1, it diverges definitely. So here is a function. Here is this function in the z plane. This is 1, that is the unit circle, represented by this infinite series inside this unit circle. And we are guaranteed that this function is infinite outside. This infinite series diverges outside. You plug in any value of z whose modulus is greater than 1, and then this series is guaranteed to give you a divergent answer. But inside this series, inside this region here, we can actually identify what this series is and sum it. We can sum it in closed form. It is a binomial series. So what is that equal to? We have f of z equal to summation n equal to 0 to infinity z to the power n mod z less than 1. So let me write that, because otherwise the series does not make sense. But I can sum this series explicitly. And what is this series equal to? It is a geometric series, so we know the answer. This is equal to 1 over 1 minus z. What that means is, if you take any point with mod z less than 1 here, like here, and you plug that into this series, find the sum, plug it into this formula, find the sum, these two are guaranteed to match point by point. But does this make sense even for mod z greater than 1? This thing here. Why not? If I set z equal to 6, for example, do not I get a value which says 1 over 1 minus 6, which is minus 1/5? It makes sense outside, right? So this form of the function, makes sense even outside, and inside this series it is guaranteed to match the Taylor series. Inside the radius of convergence, it is guaranteed to match the Taylor series. Where is the point where this blows up? Only at z equal to 1, only at this point. Only at that point it blows up. Otherwise it makes sense everywhere, all over. And you can check out that this satisfies the Cauchy-Riemann conditions everywhere except at z equal to 1. So it is an analytic function.
In fact, you can write a different power series outside.
We will write a different power series for it, we will write lots of other power series for it, but the fact is that this function has a singularity at the point 1, you can't avoid it. But everywhere else it makes sense. and inside this region of convergence, the unit circle, it matches this series, which itself does not make sense outside. So what would you call this function with respect to this series? I would call it the analytic continuation of the function defined by this series. So I think this gives you the idea of analytic continuation very clearly. You found a representation for a function, a power series, which is valid in some region, analytic in that region. You found another representation which matches this point by point, value by value, but that second representation is valid in a different region. There is an overlap region, and the second region is bigger, and it is the analytic continuation of this same function. It is just the same function here. Now suppose I had decided not to do this, but I decided to write this in a different way. Suppose I wrote this as 1 over, and I want to say find a series about this point, this is minus a half, let us say. I want a power series about the point minus a half. So what will I do? I work backwards. Write this in the following form. I write 1 over 1 minus z equal to 1 over 1 minus z plus half. So what I have done is to subtract the half, I add that half back again, so this is 3 halves, which is same as this guy here, and then I pull out this 3 halves, so it is 2/3 of 1 over 1 minus 2/3 z plus a half, okay. And this I can write back as a binomial series as long as the argument is less than 1. So I could write this as 2/3 summation n equal to 0 to infinity 2/3 to the power n z plus half to the power n. It is the same function. I started with 1 over 1 minus z, so it is the same function, but now it looks like a totally different power series because the center of this power series is the point minus half and not the point 0 as earlier. Where does this converge? This is a binomial series too. Where does it converge? Well, by the ratio test it is going to converge when modulus of 2/3 times z plus half is less than 1, or this guy modulus z plus half is less than 3 halves. It converges in that region, okay. Now what is the locus of points which look like mod z plus 1 equal to constant? It is a circle with center at minus 1 and radius equal to that constant, right. Now where is the center of this guy? At minus half. And what is the radius? 3 over 2. So this converges in a circle of this kind. But it is still stuck at this point, and that is because this master function 1 over 1 minus z, from where all these power series flow, that has got a singularity, you can't escape that. So you see the boundary of this region can be made bigger and bigger, but it will hit the singularity at this point. I can write an infinite number of series for the same function with overlap regions. In fact, I could start with this as the center, in which case it would converge in a circle like that, and then I exploit that to go here, it would converge in something like this. So I can actually go around this point all over, I can go anywhere I like by writing different power series such that each time there is an overlap region. They are all analytic continuations of each other, valid in different regions. So the lesson you have to learn is that a given function, analytic function, may have an infinite, finite or infinite number of representations, valid in different regions. Yeah.
Can we have more than one singularity for such a function?
Of course we can. Yeah, let me see that. Suppose you have 1 over z minus 1 times z minus 2. That's got a singularity at 1 as well as 2. So if you wrote a power series, you would end up with 2 singularities. You would have a power series which is valid about the point, for example, 1.5, 3 over 2, which will have singularities on both ends here. So I am going to, since that is taken me to right to the point where I want, this is something I want to emphasize, that these are all analytic continuations. We are going to spend a lot of time in this course on in analytic continuation, trying to find these master representations for functions by various tricks, but the take home lesson is that a given analytic function may have many representations. These are all representations, and each time you write a representation you have to say where it is valid. You may or may not be able to find a master representation like this from which you can find all the others, may not be possible, in general not possible, but it still does not stop you from finding analytic continuations in this form. Okay. Now one final point is the following. I am going to state this as a result and then we will come back to it, and that is the following. In this instance the circle of convergence is the unit circle. In any power series you can show rigorously that there exists a circle of convergence which may be infinite for an entire function, but there exists a circle of convergence, and the power series is absolutely convergent inside the circle of convergence, divergent outside the circle of convergence, and not much can be said except on a case by case basis about what happens on the circle of convergence. On that circle you can do all kinds of crazy things. In fact series will do crazy things. Let us take a look at this for instance. We know in this case it is infinite here, that is very clear. I put z equal to 1 and it just goes 1 plus 1 plus 1 etc. goes to infinity. Okay. Suppose you put z equal to minus 1, what happens? You have 1 minus 1 plus 1 minus 1 etc. right. So z equal to minus 1, then this guy here is 1 minus 1 plus 1 minus 1 etc. and the series oscillates. Its value will depend on whether you keep an even number of terms or an odd number of terms, but it still has some use. Even this oscillating series has some use. If I take just the first term, what is the value of the series? I retain only the first term, 1. I add the first 2, I add the first 3. So I get partial sums which are either 1 or 0, that is it, no other thing. 2 partial sums, 2 distinct partial sums. One of them is 0 and the other is 1. What is the arithmetic average of those two? Half, right. And what is the value of 1 over 1 minus z at z equal to minus 1? It is a half, right. So the point is this oscillating series, this series does not make sense on this unit circle, but it still has use, because at this point where it oscillates, if you add all the partial sums it actually gives you the value of the analytic continuity. It actually gives you the right value if you take the arithmetic average, these guys. Let us try it with this. Suppose you put the point I, then what are the partial sums? Now you have 1 plus I squared which is minus 1, plus I cubed which is minus I, plus I4 which is once again 1, and so on. So you see the partial sums are 1 plus I, and then when you add up all 4 you get 0, right. So what is the arithmetic average of those guys? 1 plus I over 2. And what happens when you put z equal to I here? You get 1 minus I, which is 1 plus I over 2 on the denominator. This sort of thing is called a Cesaro sum. You take all the partial sums and take the arithmetic average of them, and you are guaranteed that the analytic continuation of this function has that value at that point. Okay. So even divergent series, even non-absolutely convergent series will have some use. Now we saw that there was a singularity here at this point, and there is a theorem which says that every power series must have, the function which this power series represents must have at least one singularity on the circle of convergence, at least one singularity. Could be more, like I said, could be at many points. We will look at more examples of this, but it must have at least one singularity. So with that, let me stop here and we will come back to power series because they are so crucially important in all that we are going to do, because all the time our effort will be to try to find representations in terms of power series, because that will tell us, guarantee that we have an analytic function to deal with. Okay. Typically in its region of analyticity, any function, analytic function, is representable at each point by an infinite series in general, by a power series about the point z0, for instance, in a power series in non-negative powers of z minus z0, which converges absolutely inside some circle of convergence with some radius which you can determine from the coefficients, and in that region this power series inside the circle of convergence is a representation of this analytic function. And because it converges absolutely, you can take liberties with this series, you can actually integrate term by term, differentiate and so on and so forth. Okay. Now the question is, what happens on the circle of convergence? Outside the circle of convergence, of course, the power series diverges, but what happens on the circle of convergence? And I very briefly pointed out that if, for instance, at a point on the circle of convergence the series oscillates, then if you compute all the partial sums of this series and take the arithmetic mean, that turns out to be, that is called the Cesaro sum, turns out to be the value of this function which is represented by this power series at that point. Namely, it turns out to be, if you had a master representation for this function and you substituted this value of z in that master representation, then you get exactly the Cesaro sum. Okay. Now of course it is possible that the series diverges at any point on the circle of convergence and does so at more than one point. It could diverge almost everywhere on this circle of convergence. It could also converge on the circle of convergence, need not even oscillate, it could even converge. In fact, it could even converge absolutely at all points. Let me give an example. If you look at this series, summation n equal to 0 to infinity z to the power n over n, let us put n equal to 1 to infinity n squared, this thing here, this series converges, it converges absolutely for all points even on mod z equal to 1. Of course it converges absolutely for mod z less than 1, the radius of convergence is unity, and it converges even on the circle of convergence at all points everywhere. How do we see this? Well, you can sort of intuitively see that the largest value that this series can take on this circle of convergence is when z is equal to 1 itself, because then there are no phase factors, no cancellations, nothing of that kind. Each term is as large as it can get, z equal to 1, and then you have just a series 1 over n squared, but 1 over n to infinity is finite, it is zeta of 2. So this thing here says even at this point the value of the series is pi squared over 6, and everywhere else of course it cannot exceed this value, and therefore here is an instance where this function represented by this power series inside the unit circle also converges, the series converges absolutely at all points on the unit circle. You might then ask, oh, we already made a statement, I made a statement that if a function is represented by a power series inside some circle of convergence, then that function has at least one singularity on the circle of convergence, at least one singularity. I have to define what singularities are, and we will do so today, but the statement was that at least at one point there has to be a singularity of some kind. But then this looks like it is completely regular, everywhere at all points it converges absolutely, but that is deceptive, because it turns out that if you call this equal to an analytic function f of z, then you can show that f of z has in fact a singularity at z equal to 1. Okay. But it is a subtle sort of singularity, and we will see an example of this a little later more carefully. For instance, suppose the series behaved like z minus 1 log z minus 1, then in the sense of analytic function theory this log has a singularity whenever its argument vanishes. Z minus 1 of course a polynomial, nothing happens to it, it is regular, but log is a logarithmic branch point, as we will see later on. But what is the limit of this function as z tends to 1? What is the limit of z minus 1 log z minus 1 as z tends to 1? Well, the log tends to infinity and z minus 1 tends to 0, but which is stronger, you think, the power or the log? The power is stronger. So, the limit of this as z tends to 1 actually is 0. So, the singular part of this function vanishes, happens to be 0, but nevertheless it is singular at that point. So, you have to understand that singularities do not necessarily mean infinity, do not necessarily mean something becomes infinite. It is singular in the sense of analytic function theory, as we will explain what this means. In this case it has a logarithmic singularity at this point. This is related to a so called zeta function, but eventually the fact is that this theorem is still valid and you might have this strange behavior that a power series converges and converges absolutely even at all points on the circle of convergence. Even then the function represented by this series does have at least one singularity on the circle of convergence. It could have 2, 3, many singularities. It could have an infinity of singularities. For instance, suppose you took the series f of z equal to z plus z squared plus z to the power 4 plus z to the power 8, etc. So, the powers of z are 2 to the power n, as you can see. And now what is going to happen? So, this is equal to summation n equal to 0 to infinity z to the power 2 to the power n. Okay. Now, this function, this infinite series has a radius of convergence equal to 1. That is very easy to determine by the ratio test. So, it makes sense is less than infinity for mod z less than 1. Okay. On the other hand, we know that it definitely diverges if you put z equal to 1. Then of course, you have 1 plus 1 plus 1 all the way, and this function diverges, this series diverges, and the function is singular at that point for sure. So, f of 1 is a singularity of this function, f at 1 is singular. So, f of z is singular at z equal to 1. Okay. So, we see that on the unit circle there is definitely a singularity at that. Okay. But you can also write this as this same series can also be written as z plus a function of z squared, the same function of z squared. Instead of z you replace it by z squared and the remaining terms just give you f of z squared, right. This quantity must be singular at z equal to 1. Well, this part is fine, but this quantity is singular when its argument is plus 1. But when its argument is plus 1, z could be either plus 1 or minus 1. So, we deduce that there is a singularity here as well as there for this function. But you could also write this now as z plus z squared plus f of z to the power 4. And these are polynomial terms, these are harmless terms, they do not have any singularity at any finite z, right. On the other hand, this portion is singular and so is this at z4 equal to 1. So, you have these two singularities as well. And then of course, at the next stage you find that you have these singularities and so on, with the result that you are going to have a dense set of singularities on the unit circle. Okay. And there is no way in which this series, this function represented by this series can be analytically continued outside this unit circle. This circle here forms what is called a natural boundary. You can't get out of that circle at all. So, this thing here f of z has a natural boundary mod z equal to 1. Okay. And you can't do this earlier trick I mentioned, that if you had an isolated singularity somewhere here, then you can find a series here about this point which is analytic there, and then you can find the series which is analytic there and so on, and you can go out. You can't do that. There is no analytic continuation possible outside beyond this natural boundary. Okay.
Is
This
it true that suppose I went along
along the third root of unity.
Yeah.
So now that will never come in one of those things.
Yeah.
But is the theorem that there is an arbitrarily close to that there is
Yes.
a two.
There are singularities, so you cannot. You need a region. You need a finite. You need a segment.
Okay.
Yeah. So it's not possible to continue this, and this sort of series, which doesn't have a continuation outside, this kind of thing is called a lacunary series. You can construct many other such examples of lacunary series. Typically, in a heuristic way, what happens is, if there are lots of gaps in the powers, as you can see here, the next term is z to the power 16. So everything between 8 and 16 is absent, and then everything between 16 and 32 is absent, and so on. So there are lots of gaps in between in these powers, and you have very sparse powers of z, and whenever that happens you get a lacunary, you have the makings of a lacunary series. For instance, here is another example, f of z given by summation n equal to 0 to infinity z to the power n factorial. Again, this has got unit radius of convergence, and it has no analytic continuation outside this circle of convergence. So this is in fact the only representation that you have inside, valid in the entire this big circle of convergence, but that is it. You can't do anything better than that. Okay. Now these things rarely occur in physical applications, but they do occur once in a while. Natural boundaries do appear once in a very rare while, and it's good to recognize that this possibility does exist. Okay. We will say more about power series as we go along. We will see much more about power series by example.